Welcome back. For the rest of the lesson, we will test a few simple setups in Mininet. First, we'll try setting up a simple topology with 3 hosts connected to a single switch. Now you can do this by typing the following at the command line in the virtual machine that you have downloaded as part of the assignment for this week. So what this does is first runs the Mininet launcher and then says run a test ping all among the hosts in the topology. And the topology, which we specify with this topo option, is a single switch topology with 3 hosts connected to it. So this setup uses a default switch controller and a default switch. Mininet also allows you to use custom remote controllers and custom switches. Let's now go back into our VirtualBox setup, and if you remember, we had our OpenFlow tutorial virtual machine that we were using, and now I'm just going to start up that virtual machine, and now we can log back in. And we need to remember, give ourselves the host attached interface. Log back in to our Mininet environment. And now we're good to go. So you can see here, when we run that Mininet launcher with the test option and the topology option, we are asking Mininet to create a single switch topology with 3 nodes attached. Then you see Mininet doing the work of creating the network, then adding a controller, then adding the 3 hosts, adding a switch, adding the links between each host and the switch, configuring the host, starting the controller and switch, running the ping all test, and then stopping the emulation. Let's take a look at the basic Mininet command line options. So topo allows you to define a topology via the command line when Mininet starts up. So for example, we just saw a topo option where we could create a single switch topology with 3 hosts connected to that switch. The switch command line option defines the switch that you'll use in that topology. So by default, the Open vSwitch software is used, but you can define other switches. Finally, you can use the controller option to define the controller that you want to use. If this option is unspecified, then Mininet uses the default controller with a default hub-like behavior. So let's try out some other different Mininet topologies. One option you can specify is the minimal network topology. The minimal topology simply creates 2 hosts and 1 switch. So when we run this in Mininet, we can see that Mininet creates the network, adds a controller, adds the 2 hosts, adds the single switch, adds the links between the hosts and the switch, starts the controller, and starts the switch. As a second example, we can create a linear topology with 4 hosts and 4 switches. What this does is connect 1 host to each of the 4 switches, and then connects each of the switches together in a line, in a linear-like topology. So when we run this example in Mininet, we see slightly different behavior. We see, once again, the network and controller created. Then we see 4 hosts created. We see 4 switches created. Then we see, respectively, the links between each host and its respective switch, and then between each of the switches in sequence. As a third example, we can create a topology where 3 hosts are all connected to a single switch, and we have looked at that earlier in this lecture. Finally, we could use Mininet to create a tree topology with a predefined depth and fan-out. Again, we see the same type of behavior, except the links reflect a tree-like topology. Let's take a closer look at how the MN wrapper works. So, briefly, MN executes Python under the hood. It is a launch script that executes specific Python code. So, consider the option that we used before, where we said topo linear 4, which, if you recall, is a linear topology with 4 hosts, each connected to a switch, and the switches connected in a linear topology. Under the hood, that invokes the Python code that we see over here on the right. Let me just briefly walk you through this code. The first 2 lines simply import packages into Python, and the next line, linear, basically says create a linear topology, and k equals 4 says make the topology have 4 nodes. Then we invoke Mininet and we pass it the topology that we just created. We then start the Mininet emulator, and then we run ping all. Finally, we stop the emulator. We can see that code here in a .py file, and we can run it and see what happens. So, as expected, we got a topology with 4 nodes. Every node pinged every other node, and then the emulator stopped. In addition to using the MN wrapper to create topologies, you can also create your own Mininet topologies directly in Python. So here is an example with 2 hosts and 1 switch. Let's walk through this code briefly. So again, the first 2 lines import some modules that we need. The next line creates an instance of the Mininet emulator. Then we create the nodes that we will use in this network. So we have 2 hosts, H0 and H1, a switch, S0, and a controller, C0. After we create our nodes, we can create links between the nodes in the network using the add link method. So here we create a link between H0 and S0, one host and the switch, and we create a second link between H1 and the same switch, S0. So at that point, both hosts are connected to that switch, S0. We also have an example of host configuration options. Here, you can set the IP address of each host using the setIP method. Finally, as before, we start the emulation, we have all of the hosts ping one another, and then we stop the emulation. So when you run this particular piece of code, the emulation runs to completion and you immediately pop back out to the command line. If you add a line such as this, mininet CLI.CLI net before the stop, that will cause Mininet to escape to the interactive command line before the script terminates. It's not shown here, but you can also use add link to specify certain properties of the link with additional optional options, including bandwidth, delay, the maximum queue size, and the loss rate that you would wish to have on that particular link. Here is that code in the Emacs buffer as a .py script. And let's see what happens when we run that piece of code. As expected, we have two hosts and one switch, and they can ping one another. Finally, here's an example of a more complicated topology generation. You can see here that you can use the add host and add link functions inside something like a for loop, which allows you to create more complicated topologies by taking advantage of Python's scripting capabilities. Let's walk through this code in a little bit of detail. So you can see here that there is a class called single switch topo, which is a subclass of the topo class, which we have imported here. The init method is basically a constructor. So if you're familiar with object-oriented programming, that is the method that gets called when an instance of this single switch topo gets invoked. So the first thing we do is call the constructor of the parent class, and then we create the first switch, S1. Then we have a for loop that takes a parameter, n, which is passed in with the constructor, and has a default value of 2. And depending on that value of n, that determines how many times we iterate through this for loop. And for each iteration, we add a host, and we add a link that connects the host to the switch. The Python file then also has a method called simpleTest, where we invoke that class constructor to create the topology with an argument n equals 4. Meaning that we will have 4 hosts connected to that single switch topology. And as before, we create a Mininet emulator and then start the emulation. There is an additional diagnostic method here called dump node connections. And then, as before, we have the hosts all ping one another, and then we stop the emulation. Here is that piece of code in an Emacs buffer, and let us now try running that. As expected, we can see all 4 hosts connected to the switch. We can see the host connections dumped to standard output, and once again, ping all works as expected. We can augment this to run a system command like ifconfig directly on the host. Here is that piece of code in an Emacs buffer, and here is the output of that code. You can see clearly the output of the ifconfig host call. So we have covered quite a bit right here concerning Mininet in this lesson, but there are several topics we have not yet covered, which we will cover later in the course as necessary, and you can also consult the Mininet tutorial to get more information about each of these. One is how to access the file system. So it is worth noting that because Mininet uses lightweight OS virtualization, the file system that each of the hosts sees is shared. That means that if you invoke a file operation on one of the hosts, such as writing to a file, then that file would be seen on all of the other hosts in your topology. File system operations are essentially the same as they are in regular Python programming. Something that we alluded to but did not cover was how to set link speeds and properties. We will cover that in more detail later in the course as the need arises. Similarly, we will also talk more about how to configure Mininet to use custom controllers and switches. And in particular, later in the course, we will explore how the use of custom controllers and switches can change the behavior of various networks and also be used to solve different types of networking problems. We also did not cover very much about host configuration. We saw one example of a method to set the host's IP address, but there are many other methods that can also be used to set various host configuration options. We also did not cover how to conduct performance measurements inside Mininet. And again, we will cover those details as we need them throughout the course.